There are a lot of questions about tension and forces when you have a string of objects or boxes. Think of them as like a train car. And so my first example for this video is going to be ranking the acceleration of each of these boxes if the pulling forces are equal and the mass of each little box is equal. So the one thing that you probably comes to mind already is that the acceleration of each of these boxes is going to be equal for a single system. So because A is tied to B and B is tied to C, the acceleration of these will be the same, and the acceleration of D and E will be the same, and the acceleration of F will be the same. Okay, so A is equal to B, which is equal to C, and then D is equal to E and F. But how are the acceleration of these related to these? And so the thing to think about is Newton's second law, where it is the net force over the mass of the system is the acceleration. And so when I look at, let's call this system 1, when I look at system 1, I see that the net force is F sub A, but the mass of the system is 3 times the mass, 3m. When I look at, let's call this system 2, I see that the net force is the applied force, pulling it to the left, but the mass is 2 times m. And then finally, system 3, where it's just one single box, we have a total mass of just m with the same net force. And so when I look at these 3 accelerations of acceleration of system 1, system 2, and system 3, I see that acceleration of system 3 is just F over m, and then system 2 is half of that, and system 3 is 1/3 of that. So because this guy has the least mass, it will have the greatest acceleration, and then this will have the next largest acceleration, and because system 1 has the largest mass, it will have the smallest acceleration, given that the pulling force to the left is the same for all of them. The next question involving these boxes is to rank the forces of tension in the ropes if the accelerations are all the same. And so I've sort of made notes on here already that the acceleration of this system 1 is the same as the acceleration of system 2, which is the same as the acceleration of system 3. Now, I've looked at this and I sort of see that if I were to cover up some of the boxes, that some of these some of these boxes and some of these ropes look very similar to others. For example, when I look at this rope, rope 6, that rope looks pretty much like rope 5. It has the same acceleration and it's only pulling one box, which is the same as rope 3. It has the same acceleration A, and it's only pulling one box. So these 3 ropes, 3, 5, and 6, are going to have the same force of tension. So I'm going to call that force of tension on 3 is going to be equal to force of tension of 5, which is equal to force of tension of 6. Now when I look at this again, I see that rope 4 looks very similar to rope 2, because rope 2 is also only pulling 2 boxes, just like rope 4 is. And so rope 4 and rope 2 will probably have the same tension as well. So the force of tension on 4 is going to be equal to the force of tension on 2. Now that leaves us just the force of tension on 1. That is the only one that's pulling 3 boxes. So I use Newton's second law again. I like to write it like this, always to start out with the net force over the mass of the system, just because usually we're thinking about what's the acceleration. In this case, though, we're thinking about what's the net force. So acceleration times the mass of the system. In this case, we're going to be like redefining what our system is. So for example, if we were to look at rope at this first system with 3 boxes, I could think of it as rope 1 pulls 3 boxes, it pulls three masses. I can look at this, I can take off the first box and I can look at just this like little part of the system here where rope 2 is pulling, and then I can look at rope when it's just pulling 1 box, rope 3. Now, the important thing to think about is this is the net external force. And so if I'm looking at this whole thing as a system, if I'm trying to determine what's the force of tension in rope 1, the tension of rope 2 is internal to the whole system of these 3 boxes, as is rope 3. So I don't have to worry about those forces. So if I'm looking at this guy, force of tension on 1, that's going to be the acceleration times the mass of the system. And so rope 1 is pulling mass 3 masses. Let's just call each of these boxes, let's say it has a mass m. So this has 3m. So the force of tension on 1 is 3ma. When I look at this guy, when I look at 4, this is an internal force. So the force of tension in rope 4 is the only external force in the direction of acceleration. And so that's the same for rope 2. If I look at just this little part of the system, rope 3 would be internal force. So that external force is, I'm just going to rewrite it backwards, the 2 masses, right, D and E, 2 masses times the acceleration, whereas ropes 3, 5, and 6 only pull 1 mass, so just ma. So when I look at this, the force of tension in ropes 3, 5, and 6 are just mass times acceleration. The force of tension in rope 4 and rope 2 in these guys are twice as big as 5 and 3 and 6. And then the force of tension in rope 1 is 3 times as big as the other forces on 3, 5, and 6. So this is the biggest, and then this is the smallest.